All right, this lesson we're going to talk about differentiability. And so a lot of people, that word differentiable and differentiate and differentiability, that all refers to the derivative. So people see the word derivative and they try to turn it into a verb and they want to say, I'm going to derive that function. And derive is a word that we use in math, but derive is not the verb you use for derivative. The verb you want to use is differentiate. So anytime you want to perform a derivative on a function, you are differentiating that function. And so if we say a function f is differentiable at x equals c, that means the derivative of that function exists at x equals c. And differentiability is looking at whether the derivatives of things exist or whether they don't exist. All right. In order for a derivative to exist, the graph of f must have local linearity there. Basically, that means you should be able to draw a single tangent line at that point. And that tangent line will have a slope that is not undefined. So, in other words, if you zoom in on the graph far enough, it will look like a line, but not a vertical line. All right, I'm going to pull up the calculator here. That'll take a minute or two to load. So I'm going to keep talking while that gets loaded up, and then I'll kind of show you an example of what they're talking about there. Okay, so how do we tell if something's not differentiable? So there are 4 things that will tell us whether a function is not differentiable. So one of those things is a sharp turn. Sorry, this keeps popping up here. All right, one of those things is a sharp turn. So a sharp turn is any time you have like a corner like this. Okay, so an absolute value function is a good example. You'll also see this happen on piecewise functions quite a bit. So at this point right here, x equals 2, we would say this function is not differentiable at x equals 2 because there is a sharp turn there. Okay, that's one way to explain it. I'll show you a more formal way to do it with limits here in a second. Okay, but that is the only point where this function is not differentiable. F is differentiable for all other values. Okay, take x equals 1, for instance. You see how that's a line there? I'm going to draw that a little better. Okay, I can draw a tangent line there, or x equals 4 right here. I can draw a tangent line right there. Okay, so at x equals 2, though, I can't draw a tangent line. It's not horizontal, because that doesn't match up with what's happening here. So really, this is a tangent line like that, but this is also a tangent line. See how they're not agreeing with each other on the left and the right side? Remember, a derivative's a limit, and the limit must agree on the left and the right. So the slope on the left is -1. The slope on the right is +1 at that point, and that's a problem. That's why the derivative doesn't exist. So if you were to explain this explanation is perfectly okay on the AP exam. You are allowed to say sharp turn. So that's what I would suggest, and that's what I would use most times. But there are times where it's beneficial to use a more formal definition. And so we're going to use the definition of derivative, the alternative form, actually, that we used yesterday. So what you can say here is x equals 2 is our point of interest. So the limit as x approaches 2 from the left of f of x minus f of 2 over x minus 2. So that's the alternative form of the definition of derivative. And we would say that that is not equal to the limit as x approaches 2 from the right of f of x minus f of 2 divided by x minus 2. So this is the same thing as saying sharp turn. All right, it's just a more formal way to write it. All right, second way that you can tell a function is not differentiable is if it's not continuous at that point. So we learned all the ways to be not continuous. This example is showing a vertical asymptote. But we also learned about a jump. We also learned about a hole or a point discontinuity. All right, so any of those discontinuities that we've learned about, if it's not continuous, it can't be differentiable. All right, but again, this function is differentiable for all other values, everything except for x equals 2. All right, take this point right here. I can draw a tangent line right there. All right, over here, I can draw a tangent line right there. Okay, so it's only not differentiable at a single value. All right, third way is if your function has a vertical tangent line. So you really only see this on like cube root type functions because they have that curve, concave up curve going like that, and then a concave down curve going the other direction, and you get that vertical tangent right there in the middle. So this function would be not differentiable at x equals 1 because there is a vertical tangent at x equals 1, but it would be differentiable at all other points. All right, the third one is called a cusp. It is pretty much the same thing as a sharp turn, but we have a different name for it because it's two curves coming together rather than two lines coming together. Or a line and a curve would still be a sharp turn. Two curves is a cusp. Same idea though. If you were to do the tangent line on the left side, they would actually both be going vertical here like that. So it could also kind of fit into the vertical tangent line section. But basically the slope on the left side is a negative slope. The slope on the right side is a positive slope. So the slopes aren't matching up on either side, and it's not differentiable there. All right, so I wanted to show you all this in the calculator. So I'm going to graph. We'll do cube root. Just cube root of x. We'll do something simple. Okay, so what they said is if you zoom in enough, so we can do that. We can zoom in. All right, if you zoom in enough on a point, that eventually that'll look like a line. So I'm just going to zoom in here, and we get there pretty quick. All right, see how that looks like a line? And if you keep zooming in, it's going to look more and more linear the further and further and further I zoom in. All right, so I clicked too fast there to stop zooming. But you can see that basically looks like a very straight line. All right. Let me go back to the normal window. Okay, and then let's look at, this would be not differentiable at x equals 0 because it has a vertical tangent line there. And so if I zoom in on that, you'll see it also looks like a line, but it's a vertical line. All right, there we go. So I think I've zoomed in enough. Now it looks like there's a vertical line right there. You'll see that. And so that's how we could tell that that is not differentiable because the tangent line that we see is a vertical line. Okay, so that's what that definition was talking about at the top. If you zoom in over and over at x equals c on the graph of f will look like a line, but not a vertical line. All right, so I would like y'all to try this on your own. So pause the video and give this a try. You're going to identify where the function is continuous or not continuous, and you're going to identify where the function is not differentiable. Pause the video, give this a try, and then unpause and see how you did. All right, so I'm going to tackle the not continuous first. Okay, so function is continuous. I'm looking for vertical asymptotes, I'm looking for jumps, and I'm looking for holes. Okay, so I don't see any holes. I see a jump right there. So x equals 6. And that's it. All right, not differentiable. So I'm looking for the 4 things up there. Okay, so right here, I see a sharp turn. Okay, so that's x equals 3. And I'm going to write my explanation out here. All right, right here, that looks like a vertical tangent line. All right, right here, discontinuity. Remember, if a function is not continuous, it cannot be, sorry, I'm going to spell it out, discontinuity. All right, if a function is not continuous, then that means it is not differentiable. All right, and I think there's one more right here. That looks like a cusp. All right, so I'm going to scroll back up and we're going to talk about one more thing here that has to do with our discontinuity. Okay, so what we have said is that if f is not continuous, then f is not differentiable. All right, so you have to think all the way back to geometry here. All right, this is a conditional statement, if then. So what we're saying here is if not P, then not Q. All right, this is true. Okay, so there's another conditional statement that is logically equivalent to this statement right here. Okay, it's called the contrapositive. So if this is the original conditional statement, then the contrapositive is where we switch the order and we change the sign. So this one is if not P, then not Q. Our contrapositive would be if Q, then P. So let's write that out using our definition up here. So if Q is differentiable, if F is differentiable, then P. F is, oops, I forgot my F. F is continuous. This statement right here is extremely powerful. We will be using this all the time when we do our theorem questions on the free response. Okay, so there are many times where a problem will tell you f is a differentiable function, and then your theorems require that f be a continuous function. And so what you want to know, what you're able to conclude is that if f is differentiable, you know then f must be continuous as well. A very powerful relationship there, and it comes from this idea that we were told if f has a discontinuity that it is also not differentiable. And so we can use what we learned in geometry, the contrapositive, to make a second statement that's also true. If f is differentiable, then f is continuous. All right, moving on to the back. All right, which labeled points is the slope of the graph 0? All right, so you should be able to draw a horizontal line. The slope of 0 is a horizontal line here and here. So that's B and E. Positive. So we want positive slopes. Looks like here and here. C and D. Negative slopes. Looks like here and here. A and F. All right, next. F is a function that satisfies f of 2 plus h minus f of 2 is equal to 5h plus 3h squared plus 9h cubed. For all real numbers of h, find f prime of 2. Okay, this hint kind of gives away the whole problem, so I wish I had deleted that out, but I didn't. It's here. So what you should see is that just from this in the problem right there, you should recognize that. That is from the definition of derivative. You can see it right here. The only difference is they have plugged in the number 2 for x. That's why it's f prime of 2 instead of f prime of x. So what you should be able to do is rewrite this limit right here. F prime of 2 is equal to the limit as h approaches 0 of f of 2 plus h minus f of 2 all over h. And then we know that this numerator is equal to this over here. And that's very helpful because every term over here has an h. We're going to be able to divide out. So this is equal to the limit as h approaches 0 of 5h minus 3h squared plus 9h cubed all over h. Okay, that is equal to the limit as h approaches 0 of 5 minus 3h plus 9h squared. And now that we don't have a denominator anymore, we can plug in our 0 for h. Okay, we couldn't do that before, right? Because we would have gotten 0 over 0. So if we plug it in now, it's going to 0 that term out. It's going to 0 this term out. We're going to be left with our answer of 5. All right, this problem is very similar, so I'd like y'all to give that a try on your own. And then unpause the video and see how you did. Okay, so we have f of x plus y is equal to that thing for all real numbers x and y. Suppose that the limit as h approaches 0 of f of h over h is equal to 2. use the definition of derivative to find f prime of x. So I've mentioned this with limit problems. You always want to look for what's your entry point into the problem. So this question gives it away, definition of the derivative. So that's the thing you need to know, and that can be your entry point right there. All this other stuff in the problem that looks confusing, and I'm not sure how I'm going to use it yet. But I think if I can write down the definition of the derivative that we learned in our last lesson, that I could probably figure out where to go after that. So let's do that. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, so let's now look at that and look at what they gave me. So I see a limit as h approaches 0, and I have a limit as h approaches 0 here. All right, that seems like a good thing. I have an h on the denominator. I have an h on the denominator here. That's a good thing. Okay, I don't have an f of h up here. All right, but maybe I can get one somehow. All right, the other thing is this. I haven't used this. So I see something that looks very close. This is f of x plus y, and I have an f of x plus h. So remember that variables are just placeholders. You can put whatever letter you want there. Okay, so instead of f of x plus y, let's say this is f of x plus h. So what would that change over here? That would mean basically all of our y's are going to turn into h's. So I'm going to get f of x, and I'm going to get minus 4 f of h. Ooh, that's exciting, right? We wanted an f of h, and now we have one. And then plus 9xh, like that. Okay, so now I think I can just plug that in. I can plug this in for f of x plus h right here. So let's try that. The limit as h approaches 0 of f of x minus 4 f of h plus 9xh. And then I have minus f of x. That's this one right here. And then all of this is divided by h. Okay, remember when we did a definition of derivative problem, you had a few on your homework that anything that doesn't have an h attached to it has to cancel out. So I have an f of h in here. That's exciting because I know I'm going to use this limit there somehow. I have an h here, so those are going to stay, but I have an f of x, no h attached, so I better have a minus f of x to cancel it out, and I do over here. All right, now what I want to do is kind of use my limit properties and separate this out. So I'm going to pull the negative 4. I'm going to separate this into two limits at the plus sign right here. So I'm going to have this over h and then this over h, each with a limit. And then for my first limit, I'm going to pull out the negative 4. So I'm going to have negative 4 in front, multiplied by the limit as h approaches 0 of f of h over h. All right, so again, that's very exciting because that's exactly what I have right here. So I know I'm going to be able to plug a number in for that whole limit right there. Let's finish writing out our problem here before I do that, though. Okay, so this is going to sound a little weird, but it works. Okay, there are two letters here, two variables, an x and an h. Since our limit is as h approaches 0, we can treat x as if it were a constant. All right, because the variable of interest in our limit problem is an h, not an x. So just like I pulled out the negative 4 from this limit because it was a constant, and that's one of our limit properties, I can pull out a 9x out to the front. So I'm going to do that. 9x multiplied by the limit as h approaches 0 of h divided by h. Now, we could have just left it in there as well, but we would have ended up talking about how that's like a constant anyway later on. So I chose to talk about it right here. All right, so last step is to apply this last property they told me about right here. This limit's equal to 2. So I have negative 4 times 2 plus 9x. And then this limit, h and h cancel. So that's a 1 on the inside, and the limit of a constant is equal to that constant. So that's times 1. So our final answer, if we simplify and rearrange a little bit, would be 9x minus 8. All right, last problem. We're going to do a little bit of must, might, and never. So they have told us the limit as x approaches 5 of f of x minus f of 5 over x minus 5 is equal to 3. And we're going to determine if these are I keep wanting to say sometimes always, but must be true, might be true, or can never be true. Okay, they're reminding you here that this is the alternative form of the definition of derivative. F prime of c is equal to that limit. So this limit equals f prime of 5. All right, so part A says f prime of 5 is equal to 3. Well, f prime of 5 is equal to this limit. This limit's equal to 3. I'm going to go with a must right there. Second one says f prime of 5 is equal to 0. Well, we just said f prime of 5 is equal to 3, so that must be never. F of 5 is equal to 3. So I do see an f of 5 up here. We have an f of 5 right there, but we don't know what it is. Could it be equal to 3? Could be. Must it be equal to 3? No. So this one's going to be a might. F is continuous at x equals 0. Okay, so they didn't tell us anything about the function f other than what the derivative at 5 is equal to. So we know about f prime of 5, and that's it. We do not know anything about x equals 0. So could f be continuous at x equals 0? Yep, could be. We don't know. That's another might. F is continuous at x equals 5. Okay, so how'd y'all write that sentence out? We know that f's derivative at x equals 5 is equal to 3. So the derivative exists at x equals 5, which means that f is differentiable at x equals 5. And if f is differentiable, then f must be continuous. So this is a must. All right, last thing, you have to recognize this. This is something we went over in our lesson. The limit as x approaches 5 of f of x equals f of 5. This is the definition of continuity. If this is true, this is saying, this is the same thing as saying f is continuous at x equals 5. So this is actually the exact same as part E. F is continuous at x equals 5, which means this must be true. All right, hope you enjoyed our lesson on differentiability, and I will see you for the next lesson.